Okay, here's our video today on Lewis dot structures in chemistry. And all they are is diagrams, as you can see in the picture. They're diagrams that show the valence electron. So, get my pen working here. We'll just use red. So the valence electrons. What are valence electrons? Well, valence electrons are for the most part, they're the electrons in the last shell. So if we can make a crude hydrogen model here, let's say that's the nucleus, right? And so hydrogen only has one ring, or one orbit, or one energy level, or one cloud, however you want to call it. So here's that one electron. As you can see, it's showing it in the Lewis dot structure diagram. It has one electron, and it only has one electron, so it only has one shell. The electron in the last shell, and you can see helium here has 2 and so forth, and oxygen over here we have 6, right? And so on. So there are exceptions, and we'll talk about those exceptions. When you get to the transition metals, there are exceptions, so let's talk about that. So let's look at 2 of them here. We have carbon, so we have a Bohr model here, right? Niels Bohr made these Bohr models. So let's say a Bohr model. And we have carbon and we have nitrogen. So look at the dot diagram. It says that nitrogen should have 4 valence electrons. The electrons in the last shell. Well, here's the last shell, or the last orbit, last cloud, last energy level. It's right here, right? And you can count 1, 2, 3, 4. So that's why they put 4. And nitrogen in its last shell is 1, 2, 3, 4, 5, and you can count 1, 2, 3, 4, 5. So that's basically simple as we make dot diagrams. So why don't you try it yourself? Here's fluorine. Right, there's the Bohr model. What do you think? What do you think the dot diagram would be, the Lewis dot structure? And if you need more time, pause the tape. But you can see the valence electrons on the last shell, we have 1. What disappeared on us? Guess it's a water break. We have dihydrogen monoxide showing up there. So we have 1, 2, 3, 4, 5, 6, 7. So for our dot diagram, we'll have 1, 2, 3, 4, 5, 6, 7. There it is. And by the way, fluorine is very reactive. It's the most electronegative element out there, right? It loves to grab an electron, especially from the alkalis. Now, if we go back to our dihydrogen monoxide, our water molecule compound, right? We know that oxygen has 6 valence electrons, right? So let's get the pen working there. So it has 1, 2, 3, 4, 5, 6. So when the X is showing oxygens. And now oxygen, of course, you probably remember the octet rule. And it's basically simple, and on the elements want to be complete, like the neon, like the nobles, right? So oxygen just needs 2 more to be complete to get that 8, right? So right now it has 6. It needs 2 more on its second shell to get to 8. That's the basic octet rule. So it's sharing it with hydrogen. And hydrogen, by the way, it says it only has 1 ring. It just needs 2 more to be complete. So they're sharing here. This is a covalent bond, and you can look up videos. I have videos on covalent bonds. But they're sharing electrons. So we know that now, if we look at a dot diagram of that, let me get a dot diagram of that. See, as they're bonding, make sure my pen works here. So oxygen originally had 6, right? We had 1, 2, 3, 4, 5, 6, and they're sharing now. They're sharing with hydrogen in a covalent bond. So that's why you see the dot diagram like that. Now there are exceptions. I said at the beginning of the video, the exceptions are the transition metals. So if we look at iron here, so what do you think iron's valence electrons are. What do you think? Let's get my pen working here. So, I mean, we have one over here and we have one over there. So you would probably say that you would put Fe, and then you would say, well, it has two. It has two. Well, you would be right in high school. Because, in high school, chemistry teacher would say, well, our rule of a valence electron is, of course, the electrons in the highest energy level. However, when you get into college, or maybe your high school teacher will tell you, it could also be 8. Technically, it is 8. Because on its third shell, so we have 1, 2, 3, on this third shell here, there are electrons in the transition metal that are available for bonding. So it's really then another definition will be the electrons that can actually participate in chemical bonds. That could be another definition. And because iron is a transition metal, and its electrons from the third energy level are very high in energy, they're sitting very near the surface. That means that iron can use those 6 inner ones. They can use 6 inner electrons plus the 2 outer ones to get 8. So there's kind of a controversy here. So in high school chemistry, your teacher would probably just say it's 2. But technically, it is 8 because of the transition metals. All right, well, that's our video today.